All right, so what we kind of want to get into our pocket are the rules of derivations. So, what we're trying to remember and what we'll need to remember really to work our way through almost all of calculus and definitely to help you with Calc 2 um, and differential equations is knowing these derivatives and how they form will work. So, we have our definition of the derivative, which will do f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Equivalently, as I stumble on my words there, we can define this as the derivative can be the limit as some point approaches another point, and we come in from that one point to our original point in terms of x over z minus x. So both of these are acceptable ways of talking about it. We can note that we can define h as z minus x, because in this case, if we do a little bit of rewriting, we get that. But knowing this form is helpful. It's a basis that comes in for a lot of numerical methods, and we will go back to definitions when we need to look at things. So we'll start with one. A constant. The derivative of a constant is 0. And then I'm going to go to the derivative of a power, x to a power is n times x to the n minus 1. And we slowly found out that's valid for all real numbers. And a constant multiple of some function of u, we'll make it a full function of u, is equal to k times the derivative of that function. A thing to note, we will talk about our independent variable being x, and u being some function, u and v's being some function of x. Notice this is what we need to make any polynomial. If we put forth the idea that the sums or differences is equal to the derivatives sums or differences. And so these first 4 rules, which I number 3 twice, seem to have a habit of repeating a number when I change lines. Can create any polynomial. So getting out of the polynomial business, then we'll have our for a product rule where the derivative of 2 functions multiplied by each other is equal to the first times the derivative of the second plus the second times the derivative of the first. Make very clear that's a v up there. If we can always get a quotient rule out of the product rule if we treat this as to the negative first downstairs, but what we still end up getting is we get the first, or the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And we get the denominator squared. Now, the next rule, there's a couple different ways to write it. I'm going to write it as your textbook writes it, and that's the derivative of some function f composed of the function g is equal to the function f composed of the function g of x times the derivative of the g function. I actually prefer this in Leibniz notation. Dy dx is equal to dy du dx. And it's recognizing the form of the function. Either way, we're looking at a composition function, and this is otherwise known as our chain rule. And these are the things that got us to then the functions we needed to memorize. And our first memorization for us, we remembered that the derivative of e to the x was e to the x, and the derivative of a to the x was a to the x times the natural log of a. We have now added to that the derivative of natural log of x is equal to 1 over x, and the derivative of any log base a, is equal to 1 over x times the natural log of the base. Then we worked on our trigonometric functions. The derivative of sine of x is equal to cosine x. The derivative of cosine x is equal to negative sine of x. And this is something I pointed out at the time, and I'm going to continue to point out that there is a negative relationship between cofunctions. The derivative of tangent x is equal to secant x. The derivative of cotangent x is equal to secant squared x. It's funny, I said it and then I saw it, right? And this is like, I'm doing a blank page here, so I don't have my notes back and forth, so I'm kind of visually double checking myself. Chain rules, the thing I always have to look up how your book does it, because I think of it as this, and when I do the chain rule, I can do this. When I do the product rule, I will sometimes write it as u times v to the negative 1, and then, or the quotient rule, I'll write as u times v to the negative 1. I'll do the product rule, and that helps me find which one gets negative and positive on it. So, a lot of these flow out a little easily. Tangent x equals secant squared of x. Sorry, I didn't see that. But as soon as I was thinking of my co-function, it immediately popped into my head. That's one of the things is you want to write these down, and you want to get used to writing them on a blank page, just so you own them. I would firmly say, as you're doing your homework on these, try to do them without a reference sheet as much as possible. Try to internalize these. They keep coming back. And this is secant x times tangent x. And then in my derivative of my cosecant of x, again, the negative relationship between cofunctions. So negative cosecant x, cotangent x. So we get a negative sign in front. And we're going to add to this list today our inverse functions. And these I still look up. There's something we do in Calc 2 where I don't look them up as much as I used to. Your book's going to write them as arc sine of x. I tend to write sine negative 1 of x for these. And this is going to be 1 minus x squared. I think the thing that we want to note when we see these is there will be some reference to the Pythagorean theorem in them somewhere. Whenever we went and made these, there was some square root of something or squares coming across. And in Calc 2, we'll do some trig substitutions where we'll make more triangles that go backwards from here. I will do the arc function, noting that the arc function has a negative relationship to its regular function. As my rules over here. So 20, I'll do my arc tangent of x, which is equal 1 plus x squared. So 21, my cofunction arc cotangent of x is equal to negative 1 plus x squared. I want to, what we note is there is some limits onto the domains these things can come from. Sine and cosine can only come in between from negative 1 to 1, non-inclusive. Arctangent and tangent can take any real numbers. And then in our last two, the arcsecant, which can only be greater than 1 or less than negative 1, is we get the absolute value of x squared minus 1. And its cofunction will get the negative sign of this. How you relate sine and cosine to secant and cosecant with this absolute value, I've always looked for the flipping. The 1 minus x squared doesn't need the absolute value. I don't know. These are the ones I occasionally have to peek at in the book, are the arc functions. I will say in differential equations, the arc functions do become useful in a large quantity. And in Calc 2, there are certain types of integrations where we use trigonometric substitutions where we're going to need to know these. Knowing all of these as much as you can internally from memory makes some of the substitutions and changings you have to do with integral calculus a lot easier. Now, I will, as an aside, on your paper homework, let you explore that I have talked about the hyperbolic function is equal to this. So we could ask ourselves, what is the derivative of the hyperbolic function? And that's something you'll explore in your longer homework, is that the hyperbolic functions and their inverse hyperbolic functions actually end up with 12 more derivatives that you could add to this list of things that you kind of want to know. But they mirror the trigonometric functions so much that you can usually think about them as their trig functions. So just to show you, let me do this then. I could look at this as e to the x over 2 minus e to the negative x over 2 with the derivative of each. Right, using our addition rule. E is its own derivative, so that's going to give me e to the x over 2. E is its own derivative, so that's going to give me minus e to the negative x over 2, which is equal to e to the x plus e to the x over 2. And that was the other definition we had. And all of a sudden, the derivative of the hyperbolic sine is the hyperbolic cosine. And I'll let you play with those definitions. If you know these, you can create all of the other ones relatively quickly. All right, and let's play with some examples.